The talk is going to be about real-time physics of dissipation. In the context of continuum quantum field theories, we've heard a lot about second law and thermalization, both from quantum statistical mechanics and from the point of view of resource theory. This is going to be a fairly complementary view. I am a field theorist and string theorist by profession, so my intuition is largely derived by working in continuum systems. So I'll primarily talk about a sequence of papers I've been writing with my good collaborators, Felix Hallward, my former student, now at UBC, and Logan Agam, who is at ICTS in India. And there's a sort of sequence of them, and there's some previous work. The essential philosophy is explained in a paper we wrote last year. It's appropriate in this part of the world to talk about manifestos. The paper is called the Fluid Manifesto. The punchline of the construction of actions for dissipative hydrodynamics is contained in this paper. But a lot of the background material, which we didn't explain in that paper, has been developed and in these two recent papers from earlier this fall. And there's some overlapping work by my friends from MIT, Hong Liu, and his students, which I will touch upon. Okay, so the framework, or at least the question that drives my interest in this problem is, say you're a quantum field theorist, and what for decades or 5 decades ago, Ken Wilson taught us the way to think about quantum field theories in the language of effective field theory, where you start with some microscopic model, integrate out high energy degrees of freedom, and then you study the low energy effective field theory of just the relevant stuff. But the way Wilson thought about it and the way we understand quantum field theories makes perfect sense if you're in a pure quantum state, typically the vacuum of some continuum system. But much of the framework falls apart, at least not apply obviously, when you're in a mixed state. And this is the sort of issue that I find has not been very well developed, despite a lot of intuitive and very good phenomenological understanding ranging for many decades. And I think there's a very rich set of questions that could be addressed should such a framework be available, apart from intrinsic interest from just a quantum field theorist, but also for questions which touch upon issues of black holes and more generally of cosmology. And maybe the point to emphasize here is, which I will explain in a bit, is that a mixed state, as many of you know, can be purified by working in an enlarged system by just doubling the degrees of freedom, and then talking about pure states in the double tensor product Hilbert space. And this is sort of central to the Schwinger-Keldysh formalism, which Schwinger and Keldysh independently developed in the 50s and 60s, to thinking about how to do path integrals for real-time correlation functions. So my cartoon is that you have some density operator which has a bra and a ket, and you have what I call the right Hilbert space, where the ket evolves forward, and the left Hilbert space where the ket bra evolves backward. And sort of you want a path integral that sort of keeps track of both the forward and the backward evolution. And that's the general class of Schwinger-Keldysh path integrals that I will be interested in. And just as a preview for those of you who at least to inspire yourself to think about why this problem is interesting from a gravitational point of view, that black holes seem to provide a very natural avenue for implementing the Schwinger-Keldysh contour, although in most cases people tend to constellate the Schwinger-Keldysh contour with something I call the Comofield double contour. They're not quite the same, but they are morally similar. Now, just to give ourselves a benchmark, if you're sort of studying equilibrium dynamics in quantum field theory, in a density matrix, things are not so complicated. If you just go to the Euclidean framework, you basically quantum set mech, and learn about Euclidean generating functions, compute correlators, etc., etc. This is very well developed, ranging back to the Matsubara formalism way backward. And you can also do something slightly out of equilibrium. You can do linear fluctuation. Very well described in the seminal work of Pupo and friends, and they are captured by Schwinger-Keldysh correlator, the response functions and so on. So, so in some sense, if you sort of driven a system out of equilibrium, the linear response regime that Kubo formulae apply lies in the sort of, for arbitrary deviations in wavelengths away from equilibrium, but only for small amplitudes. That's why it's linear response. There's another regime which is much more interesting and applies to a wide class of field theories or a wide class of systems, which is the hydrodynamic regime, which applies for arbitrary amplitude fluctuations away from equilibrium, but only at low energies. In some sense, anybody who's learned quantum field theory has learned effective field theories. We start with various effective field theories, say for example superconductivity or Landau-Ginzburg theories, or if you sort of come from a high energy background, you've learned about the chiral model for pions and QCD. But there's a sort of prototype baby canonical effective field theory, which is the hydrodynamic effective field theory. Simply because any quantum system, any continuum quantum field theory in the low energy limit obeys the dynamics of governed by the hydrodynamic effective field theory for deviations which are long wavelength relative to global equilibrium. Okay, so and then there is this sort of vast region that we have little theoretical control. There's a lot of numerical work over the decades. And the key question is, can one develop a framework that sort of tackles these kind of general situations? I won't have anything to say about this terra incognita, but rather what I will talk about is developing a theory to talk about this hydrodynamic regime. And the way I'm going to develop this theory is by answering a question that I believe was first, that I would like to first attribute to a very inspirational paper by Feynman and Vernon from 5 decades ago, which is you start with the presentation of a microscopic quantum system in terms of the Schwinger-Keldysh path integral. So decided that you're in a Gibbs density matrix, you're in some kind of thermal state, you sort of write down the Schwinger-Keldysh contour as I sketched before, and then you say, okay, fine, I'm not interested in all that happens in this theory, I'm only interested in the low energy dynamics. So you say, fine, I'll integrate out all the high energy modes. You can do this. The problem is, if your original Schwinger-Keldysh contour happened to be one where there was just entanglement which was built up between the left and right degrees of freedom, but no interactions, the process of integration out will induce interactions. This is the point that these folks call influence functions. And an important open question which has not been answered is which influence functionals are consistent with microscopic inequality. It's very easy to write down influence functionals following a very canonical Wilsonian paradigm. The trouble is if you write down an arbitrary influence functional, you will be in tension with microscopic inequality. So you need some guiding principle of how to organize the low energy effective field theory and come up with a constraint on the allowed class of influence functions. And this is what I'm going to explain to you that we've sort of partly understood in the context of hydrodynamics, and hopefully once we can do that problem fully, we can go back and ask the general question of non-equilibrium. So that's the sort of broad picture of where this is, but I can't resist but show you a sort of a bigger picture of where this is going at this point. So what I will describe to you is this leg of the triangle of starting with the microscopic Schwinger-Keldysh construction and describing the macrophysics in the context of hydrodynamics. My ulterior motive for doing this problem is not because I want to study hydrodynamics, which is an interesting subject in its own right, but rather my underlying motive is I want to understand black hole dynamics. And there's a very interesting connection that I want to describe to you, some of you know, between hydrodynamics and black holes. It's the corollary of the ADS-CFT correspondence that some of us talked about almost a decade ago called the fluid gravity correspondence. And in the Zhao Liang mentioned, and various people in the last few years have been very intrigued of thinking about entanglement structures in quantum field theories and their connections to black hole. This is this PTFE graph that some people call ER equals EPR. ER standing for Einstein-Rosen, and EPR standing for Einstein-Podolsky-Rosen. And you'd like to sort of understand to what extent is this true, what are the sort of constraints on this kind of logic. And right now it's a slogan, it's not an equation, so you want to make that. Yes?
So I'm going to ask you, it comes as ideativity, we do not have ER equal UPR. Do you know reasons?
Let me not talk about ER equals EPR because it's not the primary aim of my talk. So let's postpone that question to the end of the discussion. Okay, so this is the big picture, and I'm happy to answer more conceptual issues related to this in the little time I have after the talk.
Excuse me, what do you mean by doubling of degrees of freedom?
I'll come back to it. So the doubling here, I simply refer to the fact in the microscopic finger Keldysh, I have some density matrix. If I want to do real-time correlation, the Keldysh contour runs forward and then runs back. So you could think of it as a single contour that runs forward and back in some complex time. Or you can think of having two copies of your system, one for the brass and one for the Kells. The microscopic state has, roughly speaking, two copies in that sense. The macroscopic theory of hydrodynamics has no such thing. And you'd like to see where these things disappear. I mean, actually, many people, particularly in the charismatic community, know this, some of these elements very well. I think the high energy community has not really appreciated this. And this is really where I'm coming to. So here's the Schwinger-Keldysh contour, just a preview of where we're going. So I want to I have some microscopic theory. Let's say, keep your favorite field theory in mind, or many body system. So I have some right degrees of freedom, I have some left degrees of freedom, and I have this contour where I start with some initial density matrix, and the density matrix is evolved forward for the right degrees of freedom and backward for the left degrees of freedom, and then you trace. So the generating functional thing that this path integral computes is this kind of generating functional. So you have a density matrix, you evolve it one way with U, you evolve it the other way with U dagger. I allow myself the freedom to turn on sources so that I can take this generating functional and then vary with respect to sources and compute correlation functions. And what the Schwinger-Keldysh formalism and the Keldysh rules give you is a way to translate this generating functional and this contour onto a sequence of time-ordered correlation functions. Okay, so in fact, time ordering is very easy to state. Time ordering is just contour ordering. Things that come before along the contour happen. Okay, so this is a very useful framework, and I emphasize that this is the only framework that you have if you want to compute time-ordered correlation functions. Every high-energy theorist learns about the Feynman contour, which just starts out in the far past and wanders all the way to the far future, but that does not give you time-ordered correlators in general. It doesn't give you all time orderings, it gives you only a class of time orderings. The key point is because of this U and U dagger here, if you translate it into an action, you see that there's the action for the right guys comes to plus sign, and the action for the left guys comes to minus sign. So when I deform by sources for operators which couple to sources on the right have a relative sign to operators which couple to sources on the left. Okay? So in some sense, you think of the enlarged operator space from a single copy to two copies of the operator algebra. The operator algebra has a signature 1 minus 1. So that's
the Hamiltonian has a jump when you come back.
Well, so okay, one way to say this is that because of this, you sort of evolve forward, evolve back, and here this turnaround you can think of as a maximally entangled state. Okay. So this is and this is at this point I'm making no assumption about what my density matrix is. Okay. There's something very interesting about this statement, something very about these contours, which is if you the whole generating function is a trace observable. Okay? So if you sort of have U and U dagger and the sources on the forward and backward legs are the same, this generating function is going to collapse to a theory of initial conditions. If UJR equals UJ left dagger, then I can use cyclicity to collapse them and use the fact that this is just trace of rho initial, which is just a statement that the equal source Schwinger-Keldysh generating function is nothing but a theory of initial conditions. But this has a consequence. It has a consequence in that if you try to evaluate correlation functions of difference operators which are the same, inserted at the same point on the left and right contours, they vanish. Any arbitrary endpoint function of a sequence of such difference operators is trivially zero. Simple consequence of unitarity. Okay? And it's a remarkable statement because it's a statement that exists a class of correlation functions that is identically zero independent of how the system is dynamically evolving. This does not happen in generic quantum systems, and there must be some underlying reason why this is the case, and we'll see how to encode this usefully. But remember that this statement is the primary signature of unitarity in the Schwinger-Keldysh quantum. A second statement is that you actually can sort of have some time-ordered correlator, and you can try to put such difference operators in the future. And you'll find that again, because you can collapse contours, you'll find that there's a largest time equation. The difference operators can't be future boosted. So these are statements that have been known since the early days, since the 60s. But and usually people just refer to them as useful word identities and move on. But we want to sort of do something useful. I don't want to talk about the microscopic theory. I want to be imagining doing things involving low energy dynamics. So I want to find an encoding of this microscopic unitarity in some useful language. And the language that, given my background, I find useful is thinking of it as a topological symmetry. Okay. So apologies to all of you who are not experts on topological field theories or haven't heard about VRST symmetries, but I'll explain what's going on. So the claim is there's a nicer way to encode unitarity simply by enlarging the operator algebra, not from 1 to 2 copies, but from 1 to 4 copies, where the two of those elements are basically, roughly speaking, left and right elements, but two others are Grassmann odd objects. So for example, imagine that your theory was some scalar field theory. You were just thinking about free scalars. Okay. So you have 2 copies of free scalars. You have 4 phi right and phi left. And in addition, you have their partners, which are Grassmann values. So they are fermionic the Grassmann objects which don't obey Fermi statistics. Okay. They're anti-commuting bosons. And so there's a psi and the psi bar, which are these anti-commuting bosons, and there's a symmetry that sort of takes you from the right scalar to its partner psi, and then another symmetry that takes you from psi to the difference. Okay. The main point is that these symmetries are also Grassmann. So when you square them, you get 0. So this is a very defining feature of topological field theories of VRST symmetries, the existence of nilpotent charges that square to 0. Now because there exist charges that square to 0, not all observables in the theory are physical. In particular, observables of this form, which are annihilated by both Q and Q bar, have vanishing correlators. So the statement which we said earlier about the difference operator correlator being 0 follows very trivially. All I have to tell you is that they are Q and Q bar exact. So anybody who knows differential geometry knows about cohomology, and these are statements about exact terms in cohomology. So Q's and Q bars, as you'll see later, are like exterior derivatives in a suitably generalized way.
So in this way, is it like enlarging your original algebra to some superalgebra?
Exactly. So what I've done here is enlarge my original operator algebra. It was just an O. It has been actually extended to a quartet, a super algebra. The main point is the supercharges here are just Grassmann downwards.
So this is like a supersymmetric quantum mechanics.
It's exactly like supersymmetric quantum mechanics. My supercharges do not have space-time indices.
Yeah. And then the state. So when you define this Q, the states that are
States that are exactly.
They are the states which satisfy OL minus OR.
Correct. Okay, so exactly what you asked yesterday, so you can basically put everything together in a compact form. You can forget about this quartet. You can say that what you have is, given your original theory, you have a single superfield O, and I prefer this mildly upgraded notation where you just put a circle on top of the field, and the average field, which is the sort of the average between the left and right contours, is the basic object, and the difference field is the top component, and the intermediate components are the Grassmann odd partners. And you can basically recover everything that you want, that you know AV is O right plus O left over. Left plus right. I mean, so again, maybe it's helpful for you to know the following. In usual literature, the average field is called a classical variable, and the difference field is called a quantum variable. I'll come back to this later. I mean, I'm just saying that in addition to the classical and the quantum variable, so in some sense, this is a sort of macroscopic variable. This is going to be the fluctuation variable, and these guys are going to be the analogs, their partners, which are there imposing in that. Okay. So that's step one. But this is just true for any quantum system, where as long as I'm computing time-ordered correlates. I'm in particular interested in thermal density matrices, and thermal density matrices have this Gibbsian form, where the density matrix itself is built in terms of Hamiltonian. And there's one useful extra condition that comes from Euclidean formalism. So Matsubara formalism tells you that the generating function of correlator, the partition function of the system, is periodic in imaginary time. Just go around the thermal circle, come back to yourself. There's a more stronger condition called the KMS condition after Kubo, Martin, and Schwinger, although historically they each independently wrote down this condition, and it was only the algebraic quantum field theorists like Haag who called it the KMS condition much later, which basically asserts that the correlation functions are analytic in an imaginary time strip of with beta. Okay. So I'm going to sort of take this, and this is the second ingredient I need. So unitarity is good, but the KMS condition is even better. So I'm going to use the KMS condition and unitarity to put things together. It's a useful.
Sorry, so the KMS and the unitarity are two separate.
They are two separate conditions a priori, because the unitarity exists for any density matrix. The KMS condition only exists for thermal density matrix. Okay. Let me tell you something later about general density matrix and KMS like conditions. Yes. So if you have other conserved charges, you think of all the other conserved charges as sort of you have some fiber bundle over your space. You have chemical potential. They just twist the boundary condition as you go around. So you have charged objects. They don't come back to themselves as you go around the thermal circle. They can come back themselves up to a twist, so that the chemical potentials take care of it. So you can very explicitly do that, but I'll pretend that I don't have charges because it's simpler to describe with other charges. But nothing changes if you won't add charges. So you can derive an interesting corollary by asking for putting together the KMS condition and the unitarity condition I mentioned before. And the statement turns out to be the following. Rather than correlation functions of difference operators, as I discussed in the past, vanishing, correlation function of the right operator minus the KMS conjugate of the left operator also vanishes. The KMS conjugate of the left operator is this guy. Okay, it's just basically the operator, but its time argument is shifted to I beta. Although I'm doing quantum field theory, I should say that I'm suppressing all spatial indices, because really all that matters for the discussion is where are operators inserted in time, registering time ordering. You can just supplement every one of my statements with spatial indices, and they'll still hold. Okay. So there's a newer set of statements, and this is also well known in thermal field theory literature, which basically says that something like an advanced correlate. So there's a name for these combinations. So in the previous case, I discussed average and difference operators. In this case, they're called retarded and advanced operators because they're usually used to compute response functions. And I've given you definitions of average and retarded and advanced operators here in terms of this KMS function.
Does OLQ still act on the L system?
It acts on the L system. It acts on the L system, but it's a imaginary time shifted argument. It'll be useful for me, rather than imagining doing this as a Hamiltonian evolution. After all, this is just a Heisenberg operator with time shift by I beta, so you can just imagine putting rho thermal on one side and rho thermal inverse on the other side. I'm going to imagine this as some kind of differential operator e to the I delta beta acting on the operator. And the infinitesimal form of this e to the I delta beta is going to be this capital delta. Just for simplicity you're writing expressions that make things easier, you can always go back and into this operator language. Okay. So these are well-known sum rules that people have discussed, and I want to now put things together. Okay. So you can sort of realize that if you want to sort of take something which is in equilibrium and take it slightly away, then there's a deviation from the KMS condition, and this is when you measured by this linear deviation operator, delta. So, but you can't have an isolated delta beta because you have these fundamental charges, this Q, SK, and Q bar, SK, these topological charges that act on your system. So every charge you have has to get folded in with the Q, SK, and Q bar, SK, and you can basically work out that what you really have is a sort of super operator in superspace, which generalizes this notion of delta beta. Okay. And you can sort of work out that these super operators satisfy their own algebra, and I've sort of written this in an algebra in a language of differential geometry. This DSK is really some version of QSK with some active-passive change. I lambda is this operator. Okay. And this is an algebra between 6 different operators that act on the entire system. Okay. These operators act on the operator algebra of a quantum field theory. So what we started with was a Hilbert space with an operator algebra. That operator algebra has these operators acting on both. So it's a graded super algebra, and this graded super algebra has an interesting structure. On this graded super algebra, you can try to do 2 successive KMS transformations, and you'll find that they satisfy some kind of bracketing relation. Lambda is some gauge, is a parameter. Is a parameter. It's a super field parameter. So basically, delta beta is roughly like 1 times delta beta, but everything has to be super field-ized. So this is the sort of analog. And if you sort of make lambdas space-time dependent, then there is an algebra which looks like some kind of Lie algebra acting on the space of parameters. So lambdas are going to be like gauge parameters, and the equation at the bottom is going to be my gauge parameter. Okay. So now, fortunately for us, we didn't have to invent the wheel. This structure is well known in the topological field theory literature. So it turns out that this whole story of these 6 generators, which I've written down here, they form this structure, and this structure has some name. It's called something, doesn't matter. But there's a much simpler version of this that many of you might be familiar with from just differential geometry. So roughly speaking, the Q's are like exterior derivative operators. Okay. So they are nilpotent, they square to 0. These QKMS and Q bar KMS, which are the super partners of this delta beta, they are like gauge transformation, BR-street transformations along superfield directions, okay, along Grassmann directions. This operator here, which we started out as delta beta, is like a Lie commutator, a Lie derivative operator on a manifold, and this other operator is like an interior contraction. So you can build up this algebra, and there's a lot of literature on using this algebra, so that's what I'm going to do. But what I want to emphasize is that what we've done here is taken microscopic entanglement and KMS condition and collapsed them into a structure of a topological superalgebra. Now the nice thing about topological superalgebras, or in general topological symmetries, is that they're robust under integrating things out. So if something it's a bit like an anomaly matching mechanism. You have some topological algebra in the UV, you integrate out all the UV degrees of freedom, and you try to